Hi, I'm Monty Zuibin, CEO of Splice Machine, and I'm here with Jack Ploshnik, and we're going to talk a little bit about unifying MLOps. And we're focusing on how feature stores can be combined with a new approach for model deployment to make data science much more productive. First, a quick little story. The reason for the project that we're going to talk about today is that in a former life, I ran the rocket fuel organization where we had a 65 petabyte big data architecture built on HBase and Spark and TensorFlow and so many other different components. And in that experience, we needed armies of engineers to put models into production and to do feature engineering. We started our project to try to make that a little bit more efficient. But today, we'll talk about a very specific piece of the MLOps reference architecture. We're going to talk first about the feature store and the data platform it sits upon, and we're going to show the benefits of streamlining that with model deployment. So, taking a step back, what's a feature store? A feature store is a centralized repository of both continuously updated raw data and transform data. The whole idea is to get data scientists to be able to leverage each other's work and to take the mundane work out of their everyday feature engineering. So they can search for features and be able to reuse them for both training and inference. It's a big topic. There are many people here at the conference and in the community building feature stores. We're so excited about it. We're writing a book on this and looking forward to incorporating much of what we learned this week and next week at TWiML. Okay, let's talk about the details of the feature store. What does it do? The feature store takes data coming from the enterprise at all different cadences, whether that's real-time events from websites and mobile apps, or just data sources from databases, data warehouses, and other external file systems, and puts that raw data through transformations. These transformations may be continuously running, they may be batch, they may be event-driven, and the data lands in the feature store. And now data scientists can search that feature store. They can form training sets from the data that's historically stored in the feature store. They can serve features in real time to models, and they can look back and look at the history of features so that they can govern and look at lineage. So there are many requirements for a feature store. It has to scale. It needs to be able to handle billions of records. It needs to be able to serve upwards to 20,000 features. And when it's serving features, it needs to do so at the millisecond time frame. And you need to be able to keep your features consistent in time. And we'll talk more about that in a few minutes. So the unique thing about our project that we'll be talking about today is that unlike traditional feature store architectures as shown in the diagram below, where you have two different engines, one for streaming data and one for batch data, and having essentially an online and offline feature store, this project that we're showing you today has a new idea. Using one store, one engine, the online feature store and the offline feature store are the same. So how do we do that? We do that with one underlying data engine that's a SQL relational database that performs both transactional workloads as well as analytical workloads, all in an ACID compliant way. For those who know databases, that means that it maintains the consistency of the database, no matter how many people are operating concurrently on that. So what are the benefits of having a single store versus an online and offline store? Having one engine is easier to provision and manage. It's easy to operate. It's also less costly to have one engine than to have many engines that you have to power with cloud infrastructure or on-premise infrastructure. It's also very easy to back up or replicate a single engine. And when you have multiple sources of data that need to be synchronized together, there often is latency that's introduced, and that's removed when you have a single engine. And a single engine gets to take advantage of features like triggers, meaning you can, as soon as new data is added to tables or changed, you can trigger events and compute on the fly in a very consistent fashion. And that allows you to have a different kind of feature store that we'll talk about today. So the underlying SQL platform is able to introspect and interrogate any SQL statements that comes to it. So if an online feature store is looking for a specific feature or looking for a single record, like a line item on an order, a cost-based optimizer using statistics knows that it's going to be manipulating fewer records and can execute that statement on a key value store. We use Apache HBase underneath the covers for this feature store. And if you're doing a feature engineering pipeline, you're doing lots of table scans that get joined together on join keys that are aggregated and potentially grouped, the cost-based optimizer knows that you're actually operating on more records and will send the instructions for that query to Spark to execute. So that's the key behind this single store. And we'll show you how that impacts the feature store in a moment. First, some concepts. So business entities that you're manipulating are in relational data tables that are all uniquely keyed with a primary key. For example, a customer. We have a notion within the feature store of feature sets. These are groups of features that are essentially updated at the same cadence. Customer spending sets of features like how much you've bought over 30 days, or demographic features like what's an income level or an address. These are organized together. And so one of the important concepts and requirements of a feature store is essentially solving the point-in-time consistency problem. What is that problem? That problem is keeping track of feature values as they change over time and keeping them consistent with each other to form training examples. So for example, let's take an e-commerce scenario where somebody is in session and logging on, doing some searches and getting some recommendations during those sessions, adding something to a shopping cart, more search, logging off. As you can see, these three features, the amount of searches they're done, the number of items in a cart, the number of products they've viewed, they're changing over time. So at this point, when a recommendation was provided, the features had a certain set of values. But at this point, they changed to 206 between these three features. Keeping track of these three values together is the point-in-time consistency problem so that you can form training sets later. Typically, without a feature store, data scientists have to do this on their own. But feature stores can do this automatically. How do they do that? Well, our feature store is a single engine. And that single engine has two important tables for each feature set. One is called the feature set table, and that holds live feature values. And the other one is a history table that has a time-indexed history of feature values. So as feature engineering pipelines are executing, where you're changing various features, that gets inserted or updated in the live feature set table. This feature set table is indexed by a primary key for the entity, like a customer ID or a transaction ID. And this is used for real-time feature serving. And you'll see Jack demonstrate this in a few moments. But the magic under the covers of this implementation is that, as I mentioned earlier, we can take advantage of database triggers. And so as you change these features in the feature set table, triggers light up and actually extract the old values of these features and place them in the feature set history table indexed with a time interval. This provides us that point-in-time consistent historical repository of features changing over time. But the data scientists didn't have to do anything. All they needed to do is write their original pipelines and change features. So all of this is taking place behind the scenes automatically in an ACID compliant way. And this is the power of a feature store. So now we're going to talk a little bit about how when you couple a feature store with deployment, there is even additional benefits with a new approach to deployment. So let's take a step back and talk about deployment in general. Many different systems do the same kind of traditional deployment with an endpoint that's potentially containerized, maybe pushed out to an endpoint manager like Amazon SageMaker or Azure ML. We're going to talk a little bit about an additional approach to model deployment. The engine that we're presenting today performs endpoint deployment, but it also does database deployment. And database deployment is taking advantage of the transactional database and its features to make model serving both transparent and efficient. So for example, when you say deploy in this system, it automatically creates a prediction table. And this prediction table has columns for every feature for that model, and also some metadata to indicate who's asking for a prediction. And when you say deploy model, code is generated to not just generate the table, but to generate, again, a trigger on this table. And when you enter records in this table with features, the model is automatically fired up and applied to these features, and predictions are memorialized in those respective records. This is extremely fast. You can populate these tables at sub-millisecond speed at scale. No extra endpoint programming is required. And this just makes it a lot easier to both deploy models faster, and it provides transparency. What kind of transparency? Well, as you saw in those tables, we memorialized every prediction. And we know for every prediction what model it was used. And then we can go back into other components of the system and look at what features were in there. And those features in the feature store have all of their history. Moreover, using a relational database underlying the feature store allows you to do time travel, where you can actually return the database back to the time when the training set was created and see exactly what the raw data looked like. So the aspiration behind having this single store, feature store, is that we can be 100 times faster for the data science scientists to get models out there and experiment, and hopefully be able to scale the data science organization with half the number of people that you would traditionally need. So with that, I'm going to pass it over to Jack and give you a little taste of what this feature store can do. And take it away, Jack.
Thanks so much, Monty. So as discussed, in the real world, there's often going to be multiple tables, join keys, or levels of aggregation necessary to arrive at any feature that you care about. The purpose of the feature store is to simplify this process. All of your different data sets feed into a central repository that the data scientist can then access. In this demonstration, I'm going to focus on the day in the life of a data scientist, seeing an already built feature store. If you would like to see how our feature store is built from the ground up, we invite you to join our workshop next week. The first benefit of a feature store is the ability to search for features. Almost all feature stores have a search bar that looks something like this. Here we have a number of customer and retail related features. We can search for deli, for example. The retailer we're looking at has a deli. We can click on one of the features, and it'll automatically build for us the feature distribution. That way, the data scientist knows what features are already available, and they don't have to duplicate any feature engineering pipelines. The second key benefit of a feature store is building training sets, specifically in that point-in-time manner that Monty discussed earlier. A point-in-time consistent training set might look something like this. We have the label that we care about. In this particular example, we are trying to determine the total customer value of a customer at our retailer. We have the customer ID and timestamp that we care about, and we have all of the features associated with that time, updated in a point-in-time consistent way. Our feature store differs from a normal feature store because we are powered by a single engine. This is powered by the training table that Monty described earlier. Let me show you how you can build a training set using the training table side of our feature store. First, we can see all of the feature sets that are available using our simple describe feature set function. Next, you can write any arbitrary SQL to define your training label. In this particular case, we have a labeled machine learning problem, and any SQL can be written to get that label. It's important to note here that the feature does not have to be a part of the feature store. The feature can come from anywhere. And it can even come from a different database using a virtual table interface or external table function. Then, in order to create that training that training set, all you have to do is use this create training view function. You specify the label, specify the primary keys and the join keys, and this function will go ahead and find for you all of the different features that are available and join them in that point in time consistent manner. The way this is generated, because we are using a single engine, is just SQL. We can see the SQL that is generated here using this get training set from view function. As you can see, we have some nasty coalesce functions, some inner joins, some subqueries. The data scientist isn't responsible for writing any of this. The feature store builds that SQL for you. A key differentiator of the single engine feature store is that this functions just like a database view. Every time you call this function, the query will generate again, and you'll get the most updated feature set. There's no need to version the data, no need to persist multiple data sets at point in times that you care about. All of this is handled automatically through the database triggers that Monty mentioned earlier. Now that we have our training set, we can do some feature selection and build any model we want using any framework that you're familiar with. The next step in our process, as Monty described, is database model deployment. Monty described what database model deployment looks like in the talk. I'm going to show you how to use it. The first part is you make an empty table inside of the database. Here we specify the schema and the table name of that database, and we specify here an MLflow run ID. Database model deployment, as we define it, means you're not restricted to the machine learning functions that exist inside of a particular database vendor. You can use any machine learning function that you want and store that in MLflow. In this case, for our database model deployment, you can use any H2O, scikit-learn, Keras, or Spark ML model that you would like. Here, we go ahead and we deploy that model, and we can see all of the different functions and triggers that are generated to create that database table. Then we can use this left-hand side real-time feature serving table to add data into that table, into that empty table we've just made. Here, using the get feature vector function, it'll generate that SQL for us, extracting the data we care about out of the feature store. Because our database has the ability to run OLTP functions, we have the ability to extract these features very, very quickly. In this particular case, these features were extracted in under 7 milliseconds. We can go ahead and run that again. And in this case, we were lucky enough to get it in an even quicker period of time. Now that we have our features from the feature set, the way to generate our features from the feature store, the way to generate predictions is as simple as an insert select statement in SQL. We insert into the empty database table that we created before, select the data from the feature store. This is simply the query the feature store generated for us. As you can see, we have inserted into the table all of these features. This prediction column is automatically generated by the feature store, along with metadata associated with that prediction. Who asked for the prediction, when, and what machine learning model was used to generate that prediction. In this case, we are inserting 2 rows and getting back 2 predictions in under 20 milliseconds. If you have streaming data, you can simply point your stream at this deployed database table. And as new data streams in, the predictions will fire, those triggers will fire, and predictions will be generated and stored in this same table. You can also use this method for batch machine learning predictions. Here we have a large table, and if we want to insert all of this data as opposed to a single row, we just insert the whole table into the deployed table that we made before. In this case, we are able to insert just under 1.6 million rows in under 45 seconds. That is, if my memory serves me right, about 35,000 predictions per second. Finally, we can tie this whole story together and use the feature store in conjunction with model deployment for monitoring model drift and feature drift. Because all of the predictions generated by our model are stored in one place, we can go back in time and look at the distribution of predictions over time, see if the model has drifted. Additionally, we can do the same for the features themselves. We can see if the we can see, because it's all stored in one place, we can see the state of the database when the model was trained and build the feature distribution at that time. Additionally, because we have all of the features themselves stored in the table, we can look at the distribution of features that the deployed model itself has seen. For this particular feature, for example, we see that the distribution of features between the trained model and the deployed model are more or less the same. For this feature, for example, we can see that there has been considerable model drift, and that's something that data scientists need to look at. Finally, imagine, for example, that a regulator or another member of your organization comes to you and say, why was a particular prediction made at a particular time? You can find a primary key associated with prediction you care about, as well as the timestamp that you care about, and go back and query the database. And it'll find for you all of the predictions that are generated at that point in time that you care about. We can see the features that were made. We can see the predictions that were generated, as well as who or what application made those predictions and when. Finally, we have the MLflow run ID. We can go back into MLflow and find exactly how this model was trained, and even potentially the Jupyter notebook used to make that model. So as I mentioned, in this demonstration, we have a day in the life of the data scientist. We invite you to our workshop where we will walk through this process in much more detail. Now I'll pass it back over to Monty.
Thank you, Jack. So some final words. The Splice Machine feature store is modular from the Splice Machine Machine Learning Manager with its model deployment that we talked about. So you can use either piece of this, and it's all open source. We welcome new members to our open source community. And as Jack showed, we've connected the feature store with database deployment, and we didn't have time to go through the integration with MLflow, but we talked about how we leverage MLflow for experiment tracking. And together, these are all orchestrated without you having to code anything together because it's Kubernetes architected. And then one theme throughout our discussion today was that there's one store, one engine. And by using a dual SQL engine, you lower your operational costs and complexity by not having an online and offline feature store. And this really adds to the transparency and lineage that you get. So we hope that you got a little view of what we're doing with our feature store and database deployment. As Jack mentioned, we really hope that you can join us for a hands-on workshop. That hands-on workshop will let you actually use our feature store and database deployment in Jupyter Notebooks with MLflow. So there'll be some great giveaways on Thursday at 9 a.m., January 28th. We really hope that you can join us. We're hiring, excuse me, we're hiring, looking for community members, and you certainly can find out more about us at splicemachine.com. Look forward to seeing you next Thursday. Thank you very much.
Awesome. Thanks, Monty. Thanks, Jack. Welcome up for questions. You've been fielding a ton of questions in the chat. I think we're all caught up on those, but folks should continue asking any questions they have. One thing that just jumps out at me is that, you know, this is clearly a very different way of thinking about the model lifecycle. And I'm just curious what takes the most adjusting for folks that want to start to use an approach like this?
Yeah, that's a great question, Sam. I think first, the whole idea of having an integrated engine does take a little bit of a transition. And the first question everybody always has is, how can I put analytical workloads and transactional workloads online and offline together into one platform? Won't they interfere with each other? Won't there be a problem with that? And I think the first and foremost thing that everyone wants to do is make sure that there's isolation amongst those JVMs and processes that are operating. So I think that's the first step that everyone always needs to get comfortable with a integrated feature store like this, and with just you know, OLAP and OLTP being combined in general in any workload. So that's point one. And also, being able to embrace SQL as a vehicle for model deployment as well as data preparation is something a little bit new, and everyone's very comfortable with their endpoint deployment, a perfectly reasonable way to deploy models, and certainly we do that in certain circumstances too. I think the idea of having models be in the database and be able to be accessed by simply inserting records also takes a little of experimentation before people are comfortable. And those are, I think, the two main areas that you see some, tilting of the head and wondering, does that really work? And that's what we need to prove in any engagement.
Great. We've got a couple of questions that have come in via the chat about the first one is getting a feature vector in the notebook in real time look like single second wall time, but you highlighted 6 millisecond CPU time as the response time. Can you elaborate on that, Jack?
Yeah, it's a great question. We're showing data in a Jupyter notebook here. Obviously, we're selecting that data back out of the table. That's what's going to take the most time, right? If this was an application, you obviously are not going to have to load the data into a Jupyter notebook. It's going to be much faster. So in terms of the precise SLAs, in terms of exactly how fast we are, we're going to go into that in a little more detail in the workshop. And we also invite people to, meet with us directly.
And adding some more color perhaps on that, Sam, with regard to single record lookups within the underlying data store, which an inference is essentially going to be using, that is very low milliseconds at the most. Sometimes it can be, as I mentioned in the chat window, at scale, a query can actually be presenting, sub-millisecond inference. This all depends on the workloads and how much of the inference may actually be in a cache, because there is a read cache within the underlying database architecture that can facilitate some of this latency analysis. I think the most important thing is, even as of yesterday, we were talking about what benchmarks would be proper for the community as a whole. And we were strategizing on helping to bring some benchmarks to the community that might vary. For example, a standard simulated set of inferencing going on at a certain throughput, maybe inferences per second, as something that is underway, and then showing how the feature ingestion and the training simultaneously, how that would impact that throughput of inference as a way of measuring a system like this. And we're really hoping that some folks in the community can help develop more benchmarks that can benchmark feature stores and benchmark models in general.
And a related question also on the performance is the kind of inverse. Is there anything you can say about the scale at which the database can continue to do millisecond retrieval?
Yes, that's a great question. And it is a horizontal scalable system. So the scaled out architecture is infinitely scalable, so to speak, obviously subject to constraints, cost constraints. But we've got customers that have 12 or so petabytes of data that are able to produce those sort of latencies, and even have even more impressive latencies with like primary key joins against many tables, like many-way joins presenting similar performance with that because of the underlying indexing infrastructure. It's infinitely scalable so that the data is sharded across multiple nodes and is able to provide that kind of performance because of that.
Great. Quick comment on, do you see this as a general purpose solution or something that is recommended for specific use cases?
Well, our goal, our aspiration is for it to be a general purpose system. It is supporting database deployment, for example, the capability that Jack showed of actually having the model be deployed within the database and be able to provide predictions in records that are inserted. We've provided that for a whole host of algorithm frameworks like PyTorch and Keras TensorFlow and Scikit and of course Spark, which is inherent to our system. And as new algorithm frameworks emerge, we'll add those. There are some places where that we need to extend the system, like some gaps within the system is there's no spatial representation as a first-class data type in the Splice Machine database yet. And that would be great to be able to learn spatial information with more explicit functions, distance functions, and being within polygons and things like that. That's a coming capability. So yes, it's general purpose, but there's always work to do.
Great, great. Thank you, Monty. Thank you, Jack. If you'd like to learn more about what Splice Machine is up to, the workshop next Thursday at 9 a.m. Pacific is your opportunity to dive into lots more detail. Thanks, guys.
Thank you very much.